Hey everybody, welcome back to another episode of Intelligence Maxing. So I have an exam in about 24 hours for my computer architecture class, and I think I might be screwed right now. There's a decent amount of work I still need to get done, so might be screwed. We'll see what happens. Gonna spend the next few hours going through what I've been able to learn, and also probably work on, if I have some paper, that would be great actually, because I would like to work on building out a little cheat sheet that we could use for the exam. So I think I'll split this. I have some flashcards, and I'm signing into my classroom account. I don't see any paper I could use though, fortunately. Actually, maybe I might be able to go to the break room. Okay. Okay, well, here is a very nice, simple 9 slide. Okay, so right through versus right back. So this is a right through versus right back cache, right? So data word ran to cache block. Okay. So I think with the write through, you're always writing to memory anytime you're writing to a block. And then write back is you're writing to memory every single time a block leaves the cache. Can read misses force writes? No, used to. Is memory busier? No. Okay, I'm not entirely sure how the caching address works. So this is actually a more in-depth lecture. Actually, this might be more helpful. I'm gonna try to look for some paper too. Yeah, did not find anything, but this should be okay. Okay, but this is something I think it's pretty important. I'm probably gonna need to add to. I might create a running list of things to add on my cheat sheet. Okay, let's do UMD, computer system architecture. exam 2 cheat sheet. Okay, so this is, I believe, you take a memory address, right? And this is how sample of how a cache reads memory address. I wonder, okay, one thing I don't fully understand is this memory address, it's stored in the program, right? Where is this? So, oh. So maybe it's probably stored in memory. So for a memory address, is this an example of a memory address that maybe does this picture show a memory address from the perspective of a cache? Let's see. So does a memory address in main memory have the same... Okay, wait, actually, does data in main memory have the same address as its cached value? Let's see. I don't know if that's the right way to put it. Okay. So if there is a 32-bit, okay, wait, actually, so if (32-bit) addresses, so, okay, so each bit, I think, if you think about the number of bytes this represents, each memory address, let's say, represents 1 byte, then you have 2 to the 32. So this means that you have, I think this means that there is 2 to the 32. Okay, so 2 to the 32, I think a gigabyte is 2 to the 30. So this is 2 gigabytes of data. Storage here. Cache have a smaller bit length address. Oh, 2 to the 2, right. Okay, so this is good now. I think one thing I was always missing was, what is this memory address actually from? So it's in main memory. And I think main memory is just the idea of like RAM. So, the random access memory. Okay, so CPU registers are the fastest. All right. I add this into latency. Actually, yeah, maybe memory hierarchy. Okay, so list out the types of memory based on the different storage data storage devices technologies that computers use based on in from longest access time to shortest access time. Right, so the slowest, so SSD slash hard drive. So that's what we think of storage. 2, you also have, think, memory, so RAM. 3 is the cache for our CPU registers. Okay. Okay, I didn't know this. So it loses all stored data when the computer's turned off. Okay. So we have the index, the tag, and the offset. So direct map cache, I think what this means is that you have an index, right? And every single index maps to a single block. Right. Number of sets is equal to the number of blocks. So I think this is the index. This is probably the tag, or this could even be the data. I think this is the tag, and this is the data here. Processor. Okay. Maybe it'd be helpful to sort of answer what this is. Block 14 octal computer. What is 14 octal? Okay, so this is 12 in decimal converted to hex. It's just C. Block 14. Okay, so that's the 12th block. But in this case we have 7 or 8. Okay, block number, mod number of sets. So, okay, it can be put in set 0. Then it'll replace one of these. So the last 2 bits of the memory block address always match the set number. So do not need to be stored as part of the address code. Okay, so this is the index and this is the tag. So I guess the cache itself really only stores the tag. Okay. So this is where it got replaced. Index. But level always consists of time to determine. Then it needs to be delivered from a block in the lower level. Okay, X. Okay, so this is what the cache memory looks like. I think this. I forgot exactly what this does. So 10, 31, it's still not a valid version of that. Oops. 10. Okay. So 10, 31. Hmm. Okay, let's see. So this is a citizen direct map cache as an example. Okay. And I want to get some clarification here. What is the valid and dirty bits? What do the valid and dirty bits do here? Okay, so this is actually very helpful. Okay, so what does a valid bit do in the cache? Initialized in the cache. I think that's probably the right way to put it. Has useful data. Okay. Block in the cache has useful data, i.e. the data within the cache has been initialized. Okay, I think that's a good way to put it. So, another way. Okay, maybe. So describe what is going on. This photo would be valid. Yeah, I think there's still something stored in memory, but it's just a random value if it hasn't been initialized. Okay. This is cache example. Four block. fine. Wait, I feel like cache is first. What does a mean when cache is first read in? Yeah, this is starting to get in the weeds a bit. It's the only way of turning it out. It's the only way to turn. It's the only way of turning the valid bit from 0 to 1. The CPU writes to a cache line as previously inbound. The cache line will be updated with the new data inbound. Okay. Usable data. Okay. 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 All right, let me see, how does caching work at a high level? So let's see if I can repeat the steps that ChatGPT was saying, right? Okay, so the CPU wants to use data for an instruction. This instruction looks first at the cache to see if the data is there. If the data is in the cache, then the CPU will read from the cache. If the data is not in the cache, CPU will read from main memory and load that into the cache. So this is a cache hit. This is a cache miss. Okay, so I think that's what's going on at a very high level. I think my question is, what are you storing in memory, right? Remember in assembly you have the load word and store word. So I think this is example could be load word, load LW instruction. Right, okay, so a load word instruction, you're loading this word that is stored in memory at some memory address. So you have to find that memory address and then bring that into your program or your process. Bring that into a register. Okay, right. So example could be a load word instruction that will retrieve the data from a memory address and then store that into a register. Okay, so I guess first the CPU looks first at the cache to see if the data is there. CPU will look up the cache, the index and tag of the memory address. It's not in the cache. I think this is actually pretty good. What happened?
I don't know, this hung up.
Huh?
Just hung up.
You said I gotta mute myself?
No, I said it just hung up.
It just hung up. Why'd you hang up on me? I'm just kidding, I'm just kidding. Say hello to the stream. I have a total of 0 people watching. Huh? I clipped that. You're on the internet forever now. Alright, bye. Okay, I actually kind of like this. CPU needs data. CPU executes an instruction that requires data from a specific memory address. It's actually good. Cache lookup. So the CPU checks the caches. Verify. Specific. Okay. CPU cache. Let's go. Thank you, ChatGPT. I appreciate the nice work. Okay. How does the CPU use the interact with the cache? Describe. With the cache. Okay, yeah, this is very good. Let's go. Executes an instruction that requires data from a specific memory address. Suppose CPU reads data in cache. And block not in cache. If it is block 41, then press overwrite block 31. Okay. Read through cache and rewrite loss image change block to cache and so that we're just false fetching blocks. Okay. God, it's not. So 3 new blocks are being loaded. So in this scenario, 3 new blocks are being loaded. So in this scenario, the CPU is executing instructions that require data stored in 3 separate memory addresses that is not stored in the cache. This data is not currently stored in the cache. Okay. Just not Wait a minute. Okay, it's not currently stored in the cache. Instructions are correct. Data stored in 3 separate. That's not currently stored in the cache. Those separate memory addresses. Reference 3 blocks. 10, 35, and 66. Each of these blocks put it into the cache valid bit switches. Okay, so the block numbers, these numbers are the tag of the memory address. Based on the index and tag of the memory address. Right, okay, so yeah. Tag of the memory address. Okay. Right, I guess that block of data, that cache line. Okay, that represents the block offset. Gets replaced by the new block. From 0 to 1. Okay, I think that this is actually a pretty good example. Example. Next. Actually. Block 31 is not stored the cache, but has the same index as block. Core 21 is switched. Okay, nice. Oops. For example. Okay. Man, some type of alarm is going off right now. I think someone ended up going through the wrong door. Now it's setting off an alarm. If it doesn't go away, then we might be screwed. Might have to dip real quick. Oh man, it's a loud ringing sound. Oh, There it is. Someone fixed it. Nice. Thank you. Thank you. Okay, wait a minute. I feel like I'm missing something here. Oh, here it is. Okay. Okay, so it can happen.
Oh, that's good. Oh, okay.
Okay. That is good to hear. Okay. I think that's a good way to put it. So now we kind of understand how this caching system works, right? You have your instructions or your list of instructions. Your CPU will execute those instructions, and whenever it needs data, so whether it's loading data, actually I think that is when you need data, you're loading some type of data from memory, then it'll first look in the cache, and the cache itself really is a place that is close to your CPU, and the way you can access it is using the memory address of each piece of data that you need. Okay. Yeah, I think that's the way to think about it. So then if you have a cache that okay, so in this example we had a direct map cache, and I think that just means that for every single block of data that you store in a cache, it's going to map to a single index or set. I guess a block of data can be thought of as a sequence of memory addresses. Each memory address usually represents one byte of data. So if you have a block size of, let's say, 256 bytes, then you have 256 memory addresses that you'll need to incorporate, or that's how big a block size is. So I think maybe initially cache is initialized based on random tags. The indexes are the same, but the tags are different, right? Okay. And every time a CPU is loading data, it'll go to the cache first. It'll see if that memory address where the data is stored matches the cache itself. Okay, so how does it check if it matches? It'll store a tag, store an index. The index is first, so that's somewhere in the middle of your memory address. I think the least significant digits are part of the offset. The most significant digits, so the digits that will change your memory address the most is the tag. Okay. So it'll check that if it's in, if you have the same index, the same tag, and a valid bit with 1, then it'll just read from that. And I think very similarly, if you're storing data, then you could just store it directly into the cache in a write-back sense, using a write-back cache. Okay. What is the cache like? I wonder if there's like an analogy for it. What is an analogy for the cache that could be helpful to memorize it? You have like the memory hierarchy, right? You have your registers, cache. Maybe this could be like your side chicks or something. Your side pieces. God. Okay, yeah. So I think about. Ooh, my screen is starting to have some problems. Okay. Yeah, I might have to unplug this real quick. Here we go, nice. Okay, let me see. Mac OS screen capture. Asus. Nice. Okay. Alright. Oh wait. I need to delete this one. There we go. Can I go use the bathroom real quick? I'll be back in a sec. Okay. Let's see. Oh wait, I think AMD earnings coming soon. Oh god. Right, AMD earnings release. Third quarter financial results. Okay. Higher sales of Epic and Instinct. So gross margins are pretty strong. Yeah, this is a bit of a side quest of sorts. Pretty strong. 122% year-over-year. Okay. When thinking about Intel, right, Intel probably competes with the CPU sales, but Instinct GPUs, yeah, that's a NVIDIA AMD thing. Okay, very interesting. Slides are cool. Okay, I could see AMD locking in the data center market from Intel. I think they are really, they have some pretty strong competitive positioning here because they're offering a CPU and a GPU itself. I think Intel, they just have their Gaudi 3, and it's not really a big complement with the Xeon processors. Let's see. Intel News. This was also a very interesting report. Intel stock. Okay, minus 1% almost. It's not a lot though, net revenue of 3 billion. Right now, I think if you look at Intel's data center revenues, it's actually around the same, maybe slightly less. So it is actually less than AMD now. Yeah, that's a rough one. Q3 23, Q2 24. Wow. Okay, quarter over quarter is 25%. Yeah, this is a lot more than what Intel made. Or this is less than what Intel made in terms of net revenues, but this is, I think, going to be higher than what Intel's going to be able to make. Statements are based on current expectations. Yeah, I'm kind of curious on Hey.
I have a program starting like in a minute.
10 minutes? Okay.
Yeah.
Alright, I'll make sure to get out of here. Thanks for letting me know. Alright. Well, thanks for tuning in to the stream today. Interesting AMD segment. Seems like the market isn't really reacting well to their earnings release, but we saw strong data center growth, so it seems like this AI trade is still going on, still pretty strong. I'd expect it to be pretty strong. So gonna finish there, and then probably we'll need to come back to this. I feel like the next part is really understanding that write back cache. If I can understand that, then that'll be very helpful. And then go through some of these questions. Okay. I want to say there's also lecture 12, lecture 11, memory hierarchy. Oh, there's also the complex instruction set stuff that's a bit confusing. Yeah, I probably need to go through that. Okay, lecture 13. Endians. Okay. And then virtual memory. All right, virtual memory, that'll be fun. So that's a pretty big one. And then cache optimization techniques. All right. So I'm gonna end this here. But thanks for tuning in, and probably go back, get some exercise in, go for a run, and then probably start the studying back again. All right. Catch you guys in the next one. Peace.